Hello everyone, welcome to our first lecture on photoelectric effect. Here we will study about the nature of radiation and matter in detail. The first topic, photoelectric effect. The name of this phenomenon is very much suggestive here. The names consist of two portions, photo and electric. All of us know the term photo means light and electric comes to the word from the topic electricity. But now we will study how these two topics can be related with each other. Before knowing or before proceeding further, we must need to know what this photoelectric effect is. Very much easy, that if you take a setup like this, thus two terminals connected with battery and galvanometer. This terminal is connected with the negative portion of the battery, so this is the negatively charged plate, or better to say cathode, and this part is connected with the positive portion of the battery, and this part must be the anode or the positively charged plate. Now usually this system is kept inside a crystal window for a reason which is beyond your syllabus. Now if we allow high frequency of light or high frequency of electromagnetic waves, we must need to proceed more than the visible region. Ultraviolet rays are perfect for this case. So if we allow ultraviolet rays of light to fall on this negatively charged portion or the negatively charged plate, we find out that this galvanometer connected with the circuit shows some amount of current flow. Now the question appears, how this thing is happening, from where this current is coming. The thing is very simply observed by Hertz. Also few other scientists like Hallworks and also performed this experiment but could not explain it. Hertz and Leonard made an advanced breed of this experiment and tried to explain it. I can show you, I have already made the picture. That was the circuit arrangement Hertz and Leonard used to tell us what photoelectric effect is. But before proceeding there, I am telling you the basic. Basically what happens, that was explained by Thomson. Thomson in 1898 told us that when this UV rays of light is falling on the negatively charged plate, this negatively charged plate, like any other plates, are contain electrons. Now these plates which are containing electrons are energized by this ultraviolet rays, and the light energy of this ultraviolet rays takes out or kicks out electron from its surface. So it basically made electrons free of its surface. And as this side of the plates are positively charged, as they are connected with the positive terminals of the battery, these electrons are attracted toward this terminal because of their Coulombic attraction. And we find out that these electrons are moving and reaching this terminal, which is causing a current flow in the circuit, and this galvanometer is basically showing that current flow. Might be very small, usually found in the microampere order, but there is a current flow happening. Now this is the phenomenon where light is causing some electricity to flow in the circuit, and this phenomenon is called photoelectric effect. Now further, this thing was studied by Hertz and Leonard, just like we were saying before. Hertz and Leonard made this circuit arrangement which is more advanced than the previous one. You can see here that first of all, there is a completely contained tube under which light rays, mostly ultraviolet radiations, are allowed. Ultraviolet radiations are allowed to fall on this negatively charged plate. Just like these radiations are allowed to come and reach one plate, and another plate is completely unaffected by it. Now we can see there is a complete setup given. One thing is that the battery is connected in the circuit, and the variable potential is given, variable resistance is given, and there is also a commutator given. Why does this commutator given? The commutator is given to change the polarity of this. Means using this commutator we can easily change the polarity of this terminal. We can either keep it positive or we can keep it negative. Clear? So we are availing the options to keep the P2 terminal either positive or negative. And this variable resistance is actually helping us, or better to say, it works as a potential divider to increase the potential value on this P2 terminal. And this microampere is kept in the circuit to actually measure the current flow happening, and this voltmeter is actually measuring how much potential we are going to apply here. So simply, what are the options available? I'm just writing down. I can change the polarity of terminal P2, this one. Clear? Second option, means I can change the potential, means I can make the voltage higher or lower, means 5 volt, 10 volt, 15 volt, whatever is desired, I can give this value. Now one more thing is that this quartz entrance is specifically designed to manipulate the incident light. I can also manipulate what kind of light will enter this tube. Now the question appears, what are the things we can manipulate? We can manipulate two things: intensity of the light and frequency of the incident light. So I got these three things here, and their variations will give us more detailed information about this photoelectric effect. We will see now. Hertz and Leonard performed the experiments to watch the variation of current flow by the variation, or by changing the amount of intensity of light, by changing the frequency of incident light, and also by changing the polarity of the second terminal and also its potential. Let's see what they found out. First of all, we will study the effect of intensity of light, means how the variation of intensity of light is affecting the photoelectric effect. Clear? See, first of all, Hertz and Leonard found out that if they increase the value of intensity, if intensity of incident light is increased, the amount of current flow increases. So if the intensity is increased, the amount of current flow increases. And how? That is very much proportional. Means That graph is proportional. If you just increase the amount of intensity, the value of current flow will keep on increasing. I hope it is clear. Now, one more thing is that now Hertz and Leonard also tried to find out more characteristics of these electrons coming out of their negative surface. So they tried a very intelligent thing. They actually tried to make the positive terminal P2 and tried to change its polarity to negative. So what happened? When light fell on the P1 terminals, the electrons emit out of it and started moving towards the terminal P2. Now usually this P2 terminal is kept positive, so these electrons are getting attracted by it. But if I just keep this terminal negative, then what will happen? Instead of attraction, they will face Coulombic repulsion. The electrons are no more getting the attractive force to move there. So they expected that if they change the polarity, they make the P2 terminal negative, then all these electrons flow will be stopped at the moment. But they found out, no, some of the electrons keeps on reaching the surface. Some of the electrons are still reaching the surface. Now if they can increase the negative potential, I already told you before that we can not only change the polarity, but we can also change the amount of potential, amount of negative voltage I will provide. Means previously if I was applying -2 volt, now I have started providing -4 volt. So if I increase the polarity, keep on increasing it, there is a certain voltage when no more electron can reach it. And the potential difference at which this happen, at the potential of P2, that must be negative, I don't need to mention that, the flow of electrons stops permanently. Is called the stopping potential. It is also known as cutoff potential. Now the question appears, at this stopping potential all the electrons are stopped, but not why before, and how the stopping potential phenomenon is working. The answer is very simple. When these light rays are bringing some amount of light energy with them, these electrons moves out of their surface. Now when these electrons are moving out of their surface, these electrons have kinetic energy. These electrons are having kinetic energy. Now the negative potential is actually repulsing them and trying to decrease their kinetic energy. But until and unless the kinetic energy is equal or lesser than the Coulombic potential, the electrons will keep on flowing, because as they are having more kinetic energy, they can move and reach the surface. But when this cutoff potential is reached or the stopping potential is reached, this kinetic energy of the electrons becomes equal to the repulsion given by the Coulombic forces. That is why this marks, if I know how much repulsion is provided by them, if I can equate with the kinetic energy of the electrons, and it is very much easy to calculate the kinetic energy of the electrons from this case. They found out that if V0 is the potential, if V0 is the potential, we know what is the potential. The potential is the amount of energy required to bring an electron from infinite distance to a point on the field. So if I know the stopping potential, The stopping potential basically marks the amount of energy required for 1 coulomb of charge. So for an electron of E coulomb of charge, E into V0 will give me the value of energy of that electron. So that is why this value E into V0 tells us the kinetic energy of the electrons. Now, so it's completely a mechanical problem. If I give the electrons more kinetic energy, the electrons will be able to penetrate further. They will be able to reach this surface again, and the current will flow again. So the Leonard and Hertz tried to increase the intensity of light. They decided that they will increase the value of intensity and expected that if they increase the intensity of the light, means more amount of light beams are given, then what will happen? The electrons will gain more kinetic energy and they will be able to flow again. Unfortunately, it was observed that no, though if I keep on increasing the intensity of light, the current flow does not start. Current flow does not start again. It was very much surprising. Later, more surprising results appear that instead of current flow, instead of intensity, if I increase the frequency of the light, if I decide to increase the frequency of the light, what happens? The current flow starts. The current flow starts in this case. So these are the phenomena they observed while studying the photoelectric effect. Now, one more thing was observed by them was that if so the things we studied from the intensity variations are changing intensity is not affecting the kinetic energy of electrons, and more importantly, changing frequency is actually varying the kinetic energy. It was very much surprising. So the scientists decided to further study how does this frequency of incident radiation or the incident light is going to vary the photoelectric effect further. They found out that increasing frequency of light does not change the amount of current flowing. Means before increasing the frequency, if the current flow was 5 ampere, if you increase the frequency, the current flow will remain 5 ampere. There is no change. Number 2, increasing the frequency increases the stopping potential. So yes, this thing again supports the thing we observed in intensity, that changing frequency is actually varying the kinetic energy of electrons. They also found out that this relationship is linear, and one more thing was found out. That thing was called work function. Scientists found out that there is a minimum frequency of incident radiation is required. A minimum frequency. It was marked as nu0. This minimum frequency was marked for each and every samples, that below a certain frequency, if incident light appears on the surface, it does not create or does not shows any kind of photoelectric effect. Even if you increase the intensity, but keep below this frequency, below nu 0. If you increase the frequency, no current flow happens. No current flow is going to happen. That's very strange. But above the minimum frequency, yes, the same intensity of light creates good amount of current flow. So it can be also studied out that the kinetic energy of these electrons are somehow related to the frequency of incident radiations. Now the question appears, how and why? And why does they look surprising? Why did they look surprising to the scientists of 19th century? It was because the classical theory or wave theory according to the wave theory of light, we all know that light actually travels like a wave, and just like more specifically like an electromagnetic wave. And like any other electromagnetic radiations, it's a transverse wave. And being a transverse wave, the amount of maximum displacement from its mean position is called its amplitude. How much the maximum displacement, I hope all of you remember that this thing is called the amplitude of this wave, right? And square of this amplitude is called intensity. Intensity is basically proportional to the square of the amplitude. So basically, if I am increasing the intensity, I am basically increasing the amplitude of the wave. I am basically increasing the amplitude. So if I increase the amplitude, it basically displaces a particle from its mean position, by a greater amount. That means it refers to a higher value of energy classically. Means increasing the intensity means I am increasing the kinetic energy of the incident radiation. Now actually what happens? It was thought that inside the surface electrons are present. The light brings kinetic energy or energy with it. One portion of the energy is used by the electron to come out of the surface, and the rest of the portion of the energy becomes the kinetic energy of it. So out of total energy, 1% goes to come out of the surface, and rest portion is going as kinetic energy. So you can see the amount of energy required to come out of a surface is always same. So if I just increase the intensity, that means increasing the energy of the incident radiation, the kinetic energy of that electron must increase. And if the kinetic energy of the electron increases, then with increase in energy, the electrons of higher kinetic energies should appear. And if electrons are having higher kinetic energy, if I increase the intensity of light, then what will happen? They will be able to reach the other side of the surface, even if I fix or increase the cutoff potential. But did that happen? Increasing intensity of light did not make reach a single electron to the other side of the surface. That was a zero current flow at then. So this is how the classical theory seemed to fail, where we thought the light as a wave, an energy wave, failed to explain the photoelectric effect in one aspect. In the next aspect, frequency of the light was always considered to be an important role playing in the velocity of light, or might be choosing the wavelength when it will change the medium. If you have studied refractive index, you will understand that the frequency always remains constant, but the wavelength varies accordingly the velocity of the light. So as an intrinsic quantity, frequency was thought, but not a characteristic quantity that is going to affect the kinetic energy of an electron. But it was found that this frequency is actually changing the kinetic energy of an electron, and there was no explanation in classical physics to that how these things are happening. And thirdly, photoelectric effect happened instantaneously. Means the moment the light falls on the surface, the current flow starts. Means there is a very low time gap between the light falling and the starting of photoelectric effect, usually find in the order of 10 to the power minus 8 second to 10 to the power minus 9 second, or more specifically 1 nanosecond order. But classically, if you think that light is like a wave, so it will come on the surface, it will share its vibrational energy with the electrons, and the electrons will get this energy and come out of the surface. That should take 10 to the power minus 3 second order timing. But you can see this thing is much faster than the calculated value of time. So it again surprises the scientists that how does this thing is happening in so much instantaneously. That's how this is so fast. There was no explanation for these three things in the wave theory. So what do you think? Is the wave theory wrong, or there is some problem with the photoelectric effect? Let's find out in the next video. Thank you everyone.